We're going to talk about the geometry of systems of equations. Let's start with one equation. And this really depends on the dimension in which we are embedding our equation into. If you have one dimension, so let's start with an equation, let's say x equals 2. So what is the representation of this equation? Well, that depends on the dimension in which we are embedding this equation into. So in one dimension, that x equals 2 will be simply a dot, a point. So that's it, just one point. That is x equals 2, no more, no less, that's it. We're assuming that this, the x is represented by numbers that are on this line. Now in two dimensions, on the other hand, the same equation, we're talking about the same, very same equation, has a different representation. So let's say there is the y-axis and the x-axis, and 2. So we want all the points for which x equals 2. By the way, all the points for which x equals 2 in 1D is just 1 point. All the points for which x equals 2 is more than 1 point. Yep, we got the same point as here, but then we got all the points above and all the points below. So this turns into a straight line. There. So a straight line, a vertical line, represents x equals 2. So this is x equals 2 in 1D, x equals 2. This vertical line represents x equals 2 in 2D. So the size of the set that is represented, the size of, that is represented by that equation increases as the dimension increases. So the size of this set is just very little, just 1 point. The size of this set, and by that I mean all the points on this vertical line, is huge in comparing to that one. But there are many more points, an infinite number of points, even though we have the same equation. So in 3D, well, I have to change the picture. I was lining those two up, so the 2 lines up with the 2. But now in 3D, we have to draw things a little differently, because typically the x-axis goes towards us. The y-axis goes to our right as we look at this, and the z-axis goes up. And by that I mean the positive numbers on the respective axis go towards us, to the right, up. Of course, the negative numbers will go away from us on the x-axis to our left as we view this picture on the y-axis, and the negative numbers go down as we look at this picture. So 2, all the points that have a coordinate of 2 on the first entry would be here, this point, and then all the points above it, and all the points across horizontally, and all the points also, up and left, or up and right, or down and right, and down and left from that point. So we will end up with a plane, that extends all over, to the right, to the left, up and down, and that would be the plane corresponding to x equals 2. Okay, so we started with a point. Now we have a line. See, the point has no dimension. The line has one dimension, dimension 1, which is embedded into a dimension 2 space. The plane has 2 dimensions, and that is embedded into a space of dimension 3. And then we have 4 dimensions, which I'm not going to draw because I don't know how to draw 4 dimensions. But what I know is that x equals 2, whatever the set is not going to be a point, is not going to be a straight line, is not going to be a plane. It is going to be a space, a whole entire space. So whatever this is, so 4 dimensions is going to be here, the space. I don't know how it's going to look like. I cannot draw it. And then we're going to have a subset that is going to be the representation of x equals 2, and that's going to be a space in itself, a 3-dimensional space, 3D space. See, this is a 0-dimensional, just this point is a 0-dimensional space. Think about that. Living inside of a 1-dimensional space. So this is a 1-dimensional space. This is, so I guess for now, we're going to interpret the dimension as the number of directions in which we can go. And here we can only go in one direction. Or, well, somebody would say, well, can you go on the opposite? That still counts as the one direction, because that is just multiplication by -1. So one direction means going to the right or to the left. That's one direction. Yeah. Or going up and down, that's still one direction. So this set has dimension 0. We cannot go in any direction. This set has dimension 1 because we can go up or down, and that counts as 1. And that space lives in a 2-dimensional space, because in 2 dimensions, we can go right or left, that's 1, and up and down, that's 2. Here, the 3-dimensional space, we can go towards us and away from us, that's 1, right or left, that's 2, up and down is 3. But the plane itself, the plane which is the representation of x equals 2, you can only go right and left, up and down. We cannot go away from us or towards us. So that is a space of dimension 2 living inside of a space of dimension 3. So we go down by 1 dimension. Dimension 1, dimension 0. Dimension 2, dimension 1. Dimension 3, dimension 2. Dimension 4, dimension 3. So x equals 2 represents one of those inside of this, but this is more complicated. I cannot even draw it. And to be perfectly honest, I don't even try. When I'm dealing with 4 dimensions or higher dimensions, I do what I called a flying with instruments. I cannot see, but the instruments, which is the math, is good enough for me to figure out what's going on. I don't have to see what is going on. I can just think of it, and that's it. Just like when, and this is abstract thinking, when somebody asks you to add 2 plus 3 and you say, well, that's 5, nobody, well, most of the students taking this kind of class say, well, I don't have to have 3 apples and then 2 apples and then count them as we did back in elementary school. You got 1, 2, 3, 4. Oh yeah, we got 5 apples. And then you do the same thing with pencils and chairs and other objects. And eventually you end up with being able to add 2 plus 3 equals 5 without thinking what you're actually adding or subtracting or whatever. So likewise here, it's cool to have those pictures, but eventually we think, oh, okay, well, I just know this is going to be a plane and or a space, and then we move from there. Oh, something else about notation or about naming things. So this is properly a plane. A plane has as properly 2 dimensions. Okay, so this x equals 2 is a plane. So this is a plane, and more properly, or more specifically, 2D plane, 2-dimensional plane. All right. So because we want to be able to go back and forth from one dimension to another, we don't necessarily always want to be too specific about the word we are using. So technically speaking, this is a line, that's not a plane. However, because the equation is the same and trying to keep things the same way, we're sometimes going to label this as a 1-dimensional plane. It kind of doesn't make sense because that is not a plane. This is a plane. But because we have the same kind of idea, we're going to call this a 1-dimensional plane. So we're going to use the word plane for all of them. That's where we're going into. So 1D plane. So there it is. So that would be a 0-dimensional plane, 0D plane, which is kind of weird. And this one is called a 3-dimensional plane, 3D plane, or a hyperplane. And then we can have a 4-dimensional plane, which is also many times called a hyperplane, a 5-dimensional plane, which simply is something like x equals 2. Yeah, I guess we could call this a 2-dimensional line going in the other direction, a 3-dimensional line, a 0-dimensional line, and this is a regular line, which is 1-dimensional, as it should be. Okay, so be prepared to call things what they're not. Yeah, and it's not too difficult as long as we are open to the idea that, okay, we can just use the same name for an entirely different object, just keeping into account that the dimensions are either increasing or decreasing. Yeah. This is kind of a silly analogy, but sometimes I come up with things like this. So this is just an analogy, as kind of a silly one. So what is August 37? Well, you're going to say, wait a minute, that doesn't even make sense. August has only 31 days. So August 37 is nonsense. Well, yeah, but if we open our mind to thinking, well, if a number can extend into the next month, even though technically it doesn't, then we can make sense of that. You know, August ends on 31st. So 32nd would be the same as September 1, and 33rd, September 2, and so forth. So August 37 could be the same thing as September 6. Why not? Just open your mind to thinking, hey, you can go on. Likewise, we can think of what is August -4, for instance. And you're thinking, wait a minute, that doesn't even make sense. Well, you got August 1, whatever that is. August negative, whoa, that gets more tricky because there's the 0. But let's keep this 0. So August 0 would be, because there's an August 1, that's the first day in August. August 0 would have to be July 31st. And then August -1 would have to be 30, July 30. And then we keep counting down. Well, I have to do this on a table because I'm losing track of what is going on. So 0, -1, -2, -3, -4. July ends on the 31st. So, and this would be the month of August. So 30, 29, 28, 27. So August -4, because of the 0, would have to be the same thing as July 27. Of course, if you tell this to somebody who's not into this math thinking, they're going to say, this is nonsense. This is just wrong. Yeah. But what I'm trying to do is show you that we can open up our mind and think of this as a line, a 2-dimensional line. This is a 1-dimensional line, and so forth. That's the only thing I'm trying to do. Let's move on with other equations. Yeah, other equations for the same kind of objects. So in 2 dimensions, so 2D, we can have 2 variables. So in 1 dimension, we have to have only one variable, whatever variable represents the 1-dimensional variable. That's it, just x. So you cannot have y unless we relabel the whole thing as y, the y-axis. But that's it, we can only have one. So points are just one. In 2 dimensions, lines or planes of dimension 1 may have one variable. If we have y equals 2, then that would represent a horizontal line going through 2. X equals 2 is a vertical line. But you could have x plus y equals 2. So x plus y equals 2. And this is back from algebra 1. That would represent this line. So just be aware that the lines don't have to be vertical or horizontal. They can be oblique. They can go in diagonally. So this point would be 2, because when y is 0, x is 2. And when x is 0, then y is 2. So this point would be 2 also. So 2, 0, to be more precise, and 0, 2. So this is a one-dimensional space embedded into a two-dimensional space. In 3D, we can also represent x plus y equals 2. And that would be a plane, not a line. So sometimes I will jump back and forth and be more precise and call this a plane and this a line. That's not a big deal. The problem gets more difficult when we go into 4 dimensions, because then what do we call this, which is the analogous of the plane, and that would be an hyperplane or a 3D plane here. But then that begs the question, well, what do we call that? Can we call it a one-dimensional plane? And as we established, yes, we may. So anyway, so how does this look like? And practice how to draw pictures this way. Yeah, so this is the XY plane, this one. And so what we are doing is, if this is the x-axis, so if you take this and rotate it and put it here, then this would be the x and the y, and this would be the 2 and the 2. And then so our line was going to go this way. But then we also have the same thing going up here. So z may be any number. It can be 1 or 2. So we have another line going above it, above, and another line above and above. So we end up with a plane that is vertical. And we start connecting this. It goes all the way down, but actually it's going to cross right through here. Yeah, the plane. So we have a vertical plane that is diagonal relative to the x z plane and the y z plane. So we have to have some reference. Yeah. So this plane, which is sort of the floor, is going to be called the xy plane. The side wall on the left is going to be labeled as the xz plane. And then this back wall is going to be labeled as yz plane. So we have 3 basic planes: the floor, side wall, back wall, xy plane, xz plane, yz plane. So this is not neither of them. It's vertical, yes, but it is diagonal compared to the xz plane and the yz plane. So this is diagonal. Yep. And then we can have a plane. In 4D, we're going to have a hyperplane, x plus y equals 2. And again, how does that look like? I don't know. I just know there's the 4-dimension space. There's going to be the x, y, z, and w axis. And then a part of it is going to be the plane. And all I know is that the coordinates x and y add up to 2. In all the points here, that's all I know. Just like here, in this hyperplane, all the coordinates of the point. So this point has coordinates, say, well, it does have coordinates 2, 0, 0. So all those numbers add up to 2, because that's what we have. Well, actually, only the first 2. But then we can have a point way up here, directly above it, and which will have coordinates 2, 0, and let's say 8. Well, still, those two, the x plus the y together, will add up to 2. We're never adding the z into the picture. Yep. So likewise, this set is going to be the set of elements such as 2, 0, and then maybe 8 and 30. I'm just making up numbers here. But what is going to be important about the points in this set, in this hyperplane, is that those two are going to add up to 0 no matter what. So you can have perhaps -10, 12, and then you can have any number you want, pi, e, whatever. Those are not relevant. What is relevant for this set, for this hyperplane, is that those two add up to 2. The rest, we don't know, and we don't necessarily care. Yeah, that is interesting. So I'm flying by instruments in the sense that I don't know what this looks like because I cannot visualize 4 dimensions, and that's okay. I personally don't have a problem with that. Some people do. Some people start analyzing and thinking and about that, and I just don't. One other example. So we can label this as example 1, the x equals 2. And then x plus y equals 2, we can label that as example 2. By the way, x plus y equals 2 in 1 dimension wouldn't make sense. We have too many variables. So it wouldn't make sense to put this in 1 dimension. We need 2 variables, so we have to have 2 coordinate systems to do that. Yeah. So example 3, what if we have, that's a 3, x plus y plus z equals 2. Okay, so first of all, this set cannot be inside of 1 dimension, and it cannot be inside of 2 dimensions because we need 3 dimensions to even be thinking of this. The easiest, for me, the easiest way to visualize this is to pretend y and z are 0. So what points are in this plane? Well, we got 2, 0, 0. And if those two are 0, then that forces x to be 2. And likewise, we have 0, 2, 0. And we have 0, 0, 2. And then because it is a plane, whenever you have a plane, you need 3 points to draw it. 3 non-collinear points to draw the plane. So 2, 0, 0 will be here. 0, 2, 0 is there. 0, 0, 2 is going to be there. So we're going to have a plane that contains this triangle. And then if we extend this triangle in all different directions, that's going to be the plane represented by this equation. Yeah. Yeah. So in general, if you have 2 planes, 2 planes, and if I don't specify that's a 2-dimensional space, 2-dimensional plane on a 3-dimensional space, well, there's a number of things that could happen. The planes could be perfectly parallel. So one and the other are like so, and they don't touch each other no matter how far they extend. So they are parallel planes. Or one plane intersects the other. So, gee, that's harder to draw, but let's see, there's one other plane, yep, that intersects with this one. This one keeps going this way. Now I think I messed up my picture a little bit because I'm not sure which way. Okay, let's draw a new picture. Yeah, it's probably easier to do it this way. So there's one plane, there's another plane that comes at a different angle. So this one extends this way. That's one. There you go. All right, that's better. So there's the 2 planes. Yep. So when they intersect each other, they're going to intersect at a line or they don't intersect. And then in mathematics, we always allow ourselves to compare things to themselves. That's a weird concept that doesn't happen in everyday life, in everyday language. We don't compare things to themselves. We never say, I look like myself. Oh, you look like yourself. That doesn't even make sense. You always compare things to other things. Oh, you look like your brother or your sister, or you look like this other person. But we never say you look like yourself. In math, we do allow that, and it's not a big deal. Whenever we have something like 3 equals 3, which is not a big deal in math, that's what we're doing. We're comparing 3 with itself. You know, in math, we don't think about this twice. We're just saying, yeah, sure, no problem. But in everyday language, that's kind of weird when we compare something to itself. So anyway, the reason why I'm bringing that up is because you could have a plane intersected with itself. So the intersection is the whole plane itself. So we could have 2 planes that are parallel, 2 planes that intersect at a line, 2 planes that intersect perfectly one on the other, which is kind of weird when we think about that, but we allow that. It's just like 0. You know, think about it, I don't know, thousands of years ago, you know, 0 didn't have a place in math because you always have 1 pen, 1 cow, 1 rock, whatever. You don't have 0. Why would you say 0? Just don't say anything if you have 0. That doesn't make sense, you know, if we're just counting things. But now we don't think twice about 0. Oh yeah, 0 is there, so it's not a big deal. So just distinguish, and that's kind of the reasoning here why we allow to go beyond something. Yeah, that's mathematical thinking. Anyway, so we got no intersection, no intersection. In this case, we have that the intersection is a line. Intersection is a line, a proper line. And here the intersection is a plane. Intersection is a plane. Yeah, and those are the only 3 things that could happen when you have 2 planes intersecting or attempting to, when 2 planes are being attempted to be intersected. This case, or that case. Yeah, this is the more interesting one. That is a little bit trivial, and this is also trivial in the sense that let's review what trivial means before we keep talking about it. So trivial in math sort of means without adding information, new information. So let me give you an example of what we mean by trivial. If I ask you to factor the number 60, and you say, well, that is 2 times 30. Okay, that's giving me more information that about 60, that it can be broken up into 2 parts. Each one of them is going to be 30. If we factor this as 6 times 10, again, I'm getting new information. I'm getting 2 numbers that are smaller than 60, each one of them, but multiplied together gives us back 60. Now somebody could say, wait a minute, can I factor it as 1 times 60? Yeah, but in that case, we call this a trivial factoring, because we're not breaking down the 60. We still have the 60. It's not adding more information than what we already had. Can we do it? Sure, but it's not adding information. So trivial doesn't necessarily mean bad. It just means that we are not adding much more information than what we already have. And there is something that is worse than trivial, which is complicating things unnecessarily. So if we say, well, can I factor it as 1/2 times 120? Yeah, but again, why do we, unless there's a purpose to it, such as when we want to, come up with a half for some reason or another, for some application. This is just making things more complicated. Not only the numbers are bigger, one number is bigger, the other number is not even an integer. So this is even worse than trivial. This is just making things unnecessarily more complicated. So why do I call those two trivial? Because especially this one, we're not really adding more information. This one is telling us more information about what's going on, how can we satisfy the two equations at the same time. Here we can add at all. So I guess this is not as trivial. This is very trivial. This is non-trivial for sure. So whenever we add more information, mathematically speaking, we say that we have a non-trivial situation. All right, so let's go down to the actual systems of equations. And let's start with an easy one. So let's say we have x plus, so 1x, we don't write down the 1, but I'm exaggerating for the moment, plus 0y, so no y, equals 3, and 0x plus 1y equals 4. By the way, we don't write the equations like that. We just say x equals 3, y equals 4. So I'm emphasizing the fact that we have this kind of situation. And one reason why we want to write it this way is because we also want to talk about matrices. So the matrix corresponding to the matrix equation corresponding to this system of equations will be 1, 0, 0, 1. That's why I have those numbers there, times x, y equals 3, 4. And we want to know the solution. And there are two interpretations. That's the one thing we want to drive in this video. The interpretations to this system of equations. Yeah, so this is going to be labeled example 5. Okay, so there are two interpretations of this system of equations. Yeah, one is going to be by looking at the rows. So 1x plus no y equals 3. That means that x equals 3. All right. So that means that x equals 3. So there's our x, y, z space. So we're going to have a plane here. Okay, when x equals 3. When actually we didn't even have to do that. Now that I think about it, let me draw it again. So back to example 5, and I'm going to copy some of this. So x plus no y, so 0y equals 3. No x plus 1y equals 4, which can be written as 1001 xy equals 3, 4. Okay, so we can think of this as a x equals 3 line in 2 dimensions. So one way to think of this, x equals 3. So we got 1, 2, 3. And this line, y equals 4. 1, 2, 3, 4. So this is x equals 3, y equals 4. And the point that satisfies both of the equations will be the unique point here, 3, 4. So that is the solution to the equation, 3, 4. All right. There is another way to think of this. So this interpretation, some people call it row interpretation. Row interpretation of the system. But somebody else could say, wait a minute, this really means 1, 0 times x, because we are doing x times 1 plus that, y times that, and then x times 0. So another interpretation is to write x, we can rewrite this as a linear combination. X times 1, 0 plus y times 0, 1 equals 3, 4. So what causes this to do that? Well, x has to be 3, as we have established that here. 3, 1, 0 plus 4, 0, 1 equals 3, 4. And the interpretation is different. That means, so the vector 1, 0 is here. So this is telling us add 3 of those, 1, 2, 3, and then add 4 of those. 0, 1 is this vector. So 1, 2, 3, 4, and we end up with a point 3, 4. So there are two interpretations. This is called or labeled the column interpretation of that system of equations. This is the column representation, as opposed to the row interpretation, which is line, line versus vector, 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 vector. Let's do a couple more of those. That sounds very interesting to me. Okay, so let's do x plus y equals 3, x minus y equals 5. Okay. By the way, the matrix representation of that is 1, 1, 1, negative 1, x, y equals 3, 5. Okay. So x plus y, so there is two representations. Be aware of that. And there are two valid interpretations of what's going on here. So as lines or planes in one-dimensional plane. So x plus y equals 3. If x is 0, then we have y equals 3. So there's a point there, another point there. So the way we represent this is by, I'm going to use a ruler here, by that. Okay, so we have a line. And then x minus y equals 5. That means that the x-intercept is going to be 5 if we just erase the y. So x equals 5. So that's going to be a little above. And then the y-intercept is going to be negative 5. So over here somewhere. So we're going to end up with this line. So where are they going to intersect? Where are they going to intersect? Here on the left. So above 3, below 5 on the left. So it's 4, negative 1, 4 going to work. Negative 1, 4, that works. Negative 1, this is 3, this is 5, negative 1, why isn't that working? So x equals 5, y is negative 5. X equals 4. Oh, x equals 4. I'm doing something wrong because I'm getting, this doesn't seem to work. Let's just double check. So x plus y equals 3, that's this line. X minus y equals 5. So x equals 5. Oh, I just realized this is y, not x. New picture. Scratch that. Boy, I can't believe I did that in this video. Of course, that's wrong. So there it is. So there's the first one, 3, 3. This is 3 and 3. And then when y is 0, x equals 5, so it'll be above, somewhere above, maybe here. Oh, here I'm doing the same thing. X equals 5, there you go. That's the x equals 5. And then y is gonna be negative 5. So we go down here and do this. There we go. Now we're good. We should be good. I hope I didn't make a second mistake on this example. There we go. Yeah. So that is 3, this is 5. The solution, which is the intersection, is past the 3, before the 5. I'm going to guess 4. And then the y-intercept should be, or the y value for the solution, I'm guessing is going to be negative 1. So 4, negative 1. Yep. 4 and negative 1 added together makes the 3. 4 and negative 1 subtracted makes the 5. So sure enough, the solution is 4, negative 1. Okay, so that is the row interpretation. If we look at the rows, that's the way to think of it. What about the column interpretation? That's a different story. Let's see. So the vector 1, 1 is this vector. So 1 to the right, 1 up. The vector 1, negative 1 is to the right and down. So I'm not going to draw it yet, but it's a vector going down this way. So the question is, how can I get to the point 3, 5, to the vector 3, 5? Okay, so let's say this is 1, 2, 3, 1, 2, 3, 4, 5. So I want to go here. But if we keep going with this vector, okay, and by the way, the solution is 4 for this vector. So we got to do 1, 2, 3. I gotta draw a better quality picture, because I just noticed that if I was going 3, I would have to go this way farther. I'm gonna draw a little bit of a grid. That's probably gonna help for the units. Okay. So if we go, so the vector 1, 1, which corresponds to this column, is this one, 1, 1. And the vector 1, negative 1, I'm going to draw it here, corresponds to this vector. They're supposed to be the same length. My squares are not very square, but they go up. That's 1, 1, and this is 1, negative 1. Can we get to the point 3, 5? So 1, 2, 3, 1, 2, 3, 4, 5. There we go. Using only this vector and this vector and this vector, no other vector. And the answer is yes. If we go 1, 2, 3, 4, okay, and if we add 1, negative 1, we were going to go down this way, but because we're subtracting, we're going to go the other way. 1, negative 1 subtracted, bingo, we are at 3, 5. So the linear combination of the vectors 1, 1 and 1, negative 1, by that what I mean is 4 times 1, 1 minus 1, negative 1 will give us the vector 3, 5. And we visualize that by going 1, 2, 3, 4. That accounts for this 4. And then minus means we're going to go not this way, which is the natural direction of the vector 1, negative 1, but minus means going the opposite direction. So if we go this way and this way, boom, we got to 3, 5. Notice that those two pictures are different. They're not the same kind of picture. There are different interpretations for the same system of equations. So there are two interpretations for systems of equations. Yeah. Let's do one that is a little more complicated. 7. Okay, so 2x plus y equals, we don't want to go too far, 3. And then x plus 2y equals 5. Nice. Okay, so, which by the way, is the same thing as 2, 1, 1, 2, x, y equals 3, 5. I just realized we may not end up with whole numbers in the solution, but that's okay. We can survive without whole numbers, with fractions. So what is one interpretation of this? Yeah, we may not, because of the x, the 2 dividing the 3. Well, we'll see what happens. Okay, so let's draw a picture for the lines. So the y-intercept is 3. 1, 2, 3. The x-intercept is going to be 1.5. 1, 2, 3, and we're going to be in the middle. So one of the lines, the first line, is going to be this one. Okay. For the second line, the x-intercept is going to be 5. 1, 2, 3, 4, 5. The y-intercept is going to be 2.5. So about there. So we're going to connect those two. So we're going to have a solution here. I'm going to guess that is half and maybe 2, half of x and 2. That will work here. So by eyeballing it, half and then 2, that works here. Half and 2, that doesn't work there. So it's not quite half and 2. We're close to half and 2. If we were to solve the system of equations, we can multiply this guy by 2. So I'm going to solve it here on the side. So we end up with 4x plus 2y equals 6. Keep this one the way it is. X plus 2y equals 5. And then we subtract the two equations. Oh, that's why, because then we end up with 4x minus x is 3x equals 1. So we're not at 1/2, it is 1/3. So the solution is 1/3, comma. So that would make it 2/3. And in order for that to work, to achieve the 3, we need 2 and 1/3. So we can use mixed numbers, 2 and 1/3, plus 2 of those make that. And if we double that, that is going to be 4 and 2/3 plus a third, that gives us the 5. So the solution is not as nice, but that's all right. That is the raw representation of that system. And I'm gonna say that is the same system. So this is the raw interpretation. How about the column interpretation? Now we gotta be a little more careful with the column interpretation. I'm actually gonna draw a little bit of a grid, because otherwise it's gonna be a little difficult. Okay, So there's the x-axis, there's the y-axis. And we have two vectors, the vector 2, 1. So that corresponds to this column, and the vector 1, 2. Now, it's interesting because if you read it across, you're going to end up with 2, 1 and 1, 2, but read them correctly, please. That's a pure coincidence. So this is the vector, and this is the other vector. And what this solution says is that if you take a third of this vector and you add 2 1/3 of this vector, we're going to end up with 3, 5. Okay, so this vector is 2, 1, 2, 1. So we have this vector, and then 1, 2 is this vector. Let me use a different writing instrument to differentiate. So if we take, because the solution is 1/3, 1/3 of this vector, so 1/3 is going to be maybe here. Well, I'm beginning, no, I think we're good. And then, well, actually, yeah, so what is the solution? Let me, so this is 1/3 of 2, 1 plus 2 and 1/3 of 1, 2. So what this is saying is take 2 of those and a little more, and a third. I was going to start with this one instead, but I'm going to use this one first because I think my drawing is going to look a little better. So take 1, 2, and 3 would be here. So about a third. Okay. And then take a third of this one on top of that. And my drawing is not very good, but it should come up to here. 1, 2, 3, 1, 2, 3, 4. Oh, no. I overshot. It's here. There we go. Not there. And I'm using a marker, so that's making things worse. Yep. Because I have to keep the same slope. Yep. So that is 1, 2, and 1/3 of this vector, 1, 1, 2, and 1/3 of this vector, a third of it, and that takes us to the point 3, 5. Whoa, that is a different interpretation than this one. Very, very different interpretation. And exactly the same thing will happen with 3 dimensions. The picture is going to be more complicated because then you're going to have 3 planes hitting each other. And so there are different ways in which that can happen. Okay. The other thing I wanted to talk about is matrices doing things to pictures. So transformations by matrices, let's call it that. Transformations by matrices. Yeah. In particular, you can rotate things, you can move things around, yeah, with matrices. So let's look at example 8. Okay. So in example 8, so this is a little bit of a different problem. We want to find a 2 by 2 matrix that rotates points around the y-axis. Okay, so this is what we mean. Say you have a point here. Yeah, let's just label it 2, 3. I want to find a matrix blank, 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 2 by 2 matrix, so that when we multiply 2, 3, I end up with a point opposite to 2, 3 across the y-axis. So that would be -2, 3. And regardless of the point you have, you want to end up with the, so this is a question mark with 4 sub-question marks, a mystery matrix, so that we end up with -2, 3 on the opposite side. So what matrix will do that? Well, let's just say we don't know. Let's use the analytic method. X, Y, Z, W times, well, in general, if you have A and B, we want to end up with opposite of A and B, because we also want to do it the other way. If we start with this, we want to end up with that. So either way, we want to reflect across the y-axis. Probably that's a better word than rotates, reflect. Points across, sorry to change that, across the y-axis. All right, so we need to solve these equations. It looks like we got 2 equations and 4 unknowns, too many unknowns. I wonder if we can just fix the x. So if x is 1, I'm just going to try things and see if they work, you know, sort of like a Sudoku kind of problem. Try numbers that would work. So we would have to have a negative a -1 here, so that becomes a -1 times a gives us -1, but then we don't want b to be involved in that coordinate, so we would have to have -1, 0. Yeah, that will do it. -1 causes the negative a to show up, but then we don't want b to be involved whatsoever, so put a 0. And then we don't want the a here, so we would want a 0, but then we want to preserve the b the way it is there. So a, b, that will cause negative a and b. So I think this method of trying to figure out, force things to happen, just kind of start pretending you have a number and see what number works, will do, as opposed to having a system of equations, because the system of equations would be, maybe let's see. So ax plus by would have to be negative a, and then za, oh, I meant a here. Sorry. So AA, oh my goodness, I can't believe I'm doing all of these mistakes in one video. AX, I had it right, I think. AX plus BY equals opposite of A. And then ZA, or AZ, plus BW equals B. See, but then we cannot cancel anything. So if we want this to be, we want, and the only time that the A shows up on the left is here. So if we want this to happen, we need a -1, and then this has to be 0. Yeah. So we have to analyze the equation itself to see what is going on to be able to come up with the matrix. So the matrix is this one. That's the matrix that would cause this to happen. Fine. So as a conclusion, the matrix is -1, 0, 0, 1. Let's do one more of those examples. Example 9. Find the 2 by 2 matrix that rotates points 90 degrees clockwise. 90 degrees clockwise. So remember, clockwise is this way. A lot of people don't have a clock with hands in it, so because we now are so digital that sometimes we forget the way the clock goes. But anyway, so that is clockwise. So let's think about this. If you have a generic point AB, let's make A short and B a little long so that we know what's going on. And we want a point in the same distance but 90 degrees down if we want to rotate. Let's see, so 90 degrees would have to be, now let's think about this. If there's 90 degrees between those two, that means that the dot product has to be 0. And so perhaps if we go B and then negative A, B, that causes this to, if we did the dot product of those two, we'll have AB. And so we have to subtract AB, but we already have A for the dot product, so that will do it. Yeah, so if you have A, B, and you go B opposite of A, that is a rotation of this point in this direction by 90 degrees. And the distance is going to be preserved, so this is a perfect rotation. Okay. So now we want to know the matrix, again, question mark, question mark, question mark, question mark, so that when we multiply with AB, we end up with B opposite of A. Okay, I should have just kept that blank so I can fill it in. Okay, so AB equals B opposite of A. Okay, so whatever is here, we'll multiply with the A, but we want to end up with a B, so let's put nothing or 0, because we don't want A to be involved here. Whatever goes here has to multiply with a B, and we do want a B, so 1 will do. Whatever is here, so let's start the multiplication. We'll multiply with A, and we want to end up with negative A, so we better put a negative 1 here. And then whatever is here is going to multiply with a B, but we want no B here, so let's put a 0 there. So that will do. If we rotate AB with this matrix, that will cause the point to rotate 90 degrees. Yeah. So so the matrix, the wanted matrix, is 0, 1, negative 1, 0. Yep. And this has more consequences. That means that if you have a parabola, y equals x squared, we can actually come up with the corresponding parabola that switches, that rotates 90 degrees. That's not too exciting, I suppose, because we know what it is, but so we can come up with a, so this is the regular parabola, and we want it to be this way. So according to this, what we have to do is change all the x's with y's, and then the y with negative x. So negative x. I would have to redo this. No. I think the x would have, the y's have to be changed into negative x's. Boy, am I getting confused with this or not? The point is, I think we're going to end up with negative y squared, and that causes this parabola. All right, that was just an expansion on the rotations. And there's a whole little branch of algebra that talks about rotations, and then we can rotate parabolas 45 degrees, and those are kind of cool to watch. But then they're not functions anymore, just like this one is not a function because there's actually two y's going on here. Anyway, this is it for this section about the geometry of systems of equations. And we'll stop here.